Hello, my name is Stephan Drawsand. I'm a computer engineering major, and I'm from Houston, Texas.
Hello, my name is Rodney Jones. I'm a computer science major, and I'm from Houston, Texas.
Hello, my name is Tim Reed. I'm from Cypress, Texas. I'm a mechanical engineering major.
I'm Liam Salazar, Jr., computer science major.
Hi, my name is Rodney Jones, and in this video we're going to be demonstrating a problem dealing with capacitors. Capacitance is typified by a parallel plate arrangement and is defined in terms of charge storage. In order to find the equivalent capacitance, which we're going to do in this problem, you will need to find the magnitude of the charge stored and the voltage applied to the plates, which is the Q over the V is equal to C. Capacitors are basically a battery that will transport charge from one plate into the other until the voltage produced by the charge buildup is equal to the battery voltage. So we're going to go ahead and get into this example right now.
So we have a voltage source of 42 volts. C1 and C2 are parallel with the voltage source, and C3 and C4 are parallel with all of those. These are our values for C1, C2, C3, C4. C1 we have 4.03 microfarad. C2 we have 1.29 microfarad. C3 we have 27.5 microfarad. And C4 we have 6.43 microfarad. Our goal is to find CEQ. So to find the equivalent capacitance, we have to condense this whole entire circuit into one really simple circuit. Our way of solving it is we could view C3 and C4 as series because they're directly connected to each other. To do series in capacitors, you could do 1 plus C1 plus 1 over C2 all the way up to 1 over CK, and then the reciprocal of that. In our case, we have 1 over 27.5 microfarad for C3 plus 1 over 6.43 microfarad, get the answer, and then the reciprocal of that answer, and we're going to get 5.21 microfarad. Now, once we condense that, we could just do this. C3, 4 is 5.21 microfarad. We could also view these two right here, C1 and C2, as parallel because there's a junction in between, meaning that the current can either go up or straight ahead, up or straight ahead. So we have it down here for C1, C2 is in parallel. Parallel capacitors you could just add across. So in this case, C1 plus C2. We have 4.03 microfarad for C1 plus C2 is 1.29 microfarad. If we just add those straight across, it's going to be 5.32 microfarad. Now to get CEQ, let's just actually condense this back into what we talked about. There's going to be bloopers below. For CEQ, we could just add them straight across. So C34, which is 5.21 microfarads, plus C12, 5.32 microfarad. Our equivalent capacitance is 10.53 microfarad.
So basically, we're continuing from the last problem. We're just going to find the charge for capacitor 1. And so to find that, we will need to first convert capacitor 1 to farads, because right now it's in microfarad. So convert that to farads will be 4.03 times 10 to the negative 6 farads. And we already know our voltage is 42. So if we put this in the calculation, we'll get this. Let me put this in the calculator just for reference.
So for part 3 of this problem, we're asked to find the charge on the 6.43 microfarad capacitor on the lower right. So we know that charge is equal to Q times CV, which is the capacitance times the voltage. We found from the previous problem that since we have two capacitors in series, we're going to add the inverses of them together, and that's how we got the value from our previous problem. Now, plugging it into our charge equation, we're going to take 5.21 microfarads times the 42 voltage, and we get the answer 218.82 microcoulombs.